Hello and welcome everybody to the first webinar of the Horizon 2020 project Restore. I'm glad that you joined us today to learn more about the Restore concept to decarbonize district heating and cooling, and also to gain insights into new scientific findings about thermochemical energy storages, as well as reversible organic Rankine cycles. My name is Tilo Walzer from the Steinbeis Research Institute for Solar and Sustainable Thermal Energy Systems, SOLITES. Our main role in Restore is to coordinate the dissemination and communication, so that I'm happy to organize and moderate this webinar today. One of our main interests at SOLITES is technologies that allow for decarbonizing the district heating and cooling sector. So the Restore concept to combine a thermochemical energy storage with a heat pump that can be operated reversibly as organic Rankine cycles is a potential solution to integrate high shares of renewable energy sources in district heating and cooling networks. Our experts on those technologies will explain you today how this combination works in detail and present some of the results that have been obtained in the first 30 months of the project. Before we start with the first presentation, I want to quickly inform you that we have a Q&A section at the end of this webinar. So if you have any questions during either of the presentations, please post it using the Q&A feed. Then those questions will be answered after the third presentation. So I also want to inform you that this webinar is being recorded and all the attendees' cameras and microphones are turned off by default. First presentation is about the Restore overall concept presented by Francisco Cabello Nuñez from the National Renewable Energy Center of Spain, CENER. Francisco is the coordinator of the Restore project, and he's also expert on simulation for solar collectors, CSB plants, as well as thermal energy storage systems. He has published many peer-reviewed papers on those topics, and I'm very glad that you will bring your expertise into this webinar, Francisco. So the stage is yours to share your screen now and to do your presentation.
Thank you very much, Tilo, for this introduction. I'm going to share the screen. Give me 1 second. Well, so let me know if you can see my screen, please.
We can see it.
Okay, thank you very much for your introduction, Tilo, and welcome everyone to this first webinar about the Restore project. This project is an European research project with 11 different partners, and at this moment it has a duration of 4 years, but we are in month 30, which is between 2 and 3 years of activities. Well, in this presentation, I'm going to try to give you a general overview about the project. First, mention the project motivation, then the objectives, the overall concept, then some information about the activities that we carry out, the validation plan of the technology that we propose it, and also the replicability analysis that we will study in the project, and finally introduce you the consortium that is involved in this research. So, well, first of all, regarding the motivation mentioned, that in the European residential sector covers around 25% of the final energy consumption, corresponding to around 280 megatons of equivalent oil per year. And the largest share is used for space and water heating, around 80%. And a large fraction is covered by fossil fuels burned in conventional boilers. In the specific case of district heating, it mainly relies on natural gas, 37%, coal, around 25%, a small fraction of this energy is covered by renewable energy sources, around 22% in Europe. And one of the main reasons for that is the unpredictability of these sources, and also the lack of dispatchability on daily and seasonal basis. Well, so as a result, the space heating sector releases around 840 megatons of CO2 per year, which represents approximately around 27% of the total CO2 emissions at European level related with energy activities. So considering that, and considering as a reminder that decarbonization is a global trend, in our case, the European policies are oriented to get a climate neutral economy in our region in the future. Considering that also that the district heating and cooling networks have relevant potential to reduce the emissions in the space heating and cooling sector, the conclusion is direct, is that the decarbonization of this network is a must in order to fulfill the European objectives. However, innovative and disruptive solutions are required to increase the integration of sustainable energy sources in the district heating and cooling networks. So in this context, we start with the restore approach before starting the project, and our first step was the identification of these barriers that do not allow the penetration of renewable energies, but in general sustainable energy sources in the district heating network. And the first barrier that we identified is the limited dispatchability of these sustainable energy sources. The second barrier that we identify is that the current solutions are not adaptable to different particularities containing different technologies and energy sources. And as direct consequence of that, their replicability is quite limited to be applicable in different European regions. Then we identify the challenges to overcome these barriers. And the first one was to develop energy storage solutions for daily and seasonal storage. The second one was to develop solutions that allows an efficient and effective integration of the different sustainable energy sources in this network. And the final one was a find solutions that are adaptable to the different conditions demanded by the different regions of Europe. So after identify the challenges with Restore, we try to give response to them. And for that, we propose first the use of a competitive thermochemical energy storage. Second, we propose the use of the heat pump and the organic Rankine cycles to allow the introduction of different renewable energy sources, but also waste heat recovery in the district heating networks. And here in our project, of course, we analyze the replicability of this idea. It's something that I will introduce you later. Well, so after this analysis, we define the restore global objective, which is to develop a solution based on the combination of two innovative technologies. On the one hand, the thermochemical energy storage, and on the other hand, the organic cycles, to integrate the different sustainable energy sources, like different technologies concerning renewable energy, but also waste industrial heat, and integrate it with daily and seasonal energy storage, not only storage of electricity, but also energy in the form of heat, in order to increase, finally, the environmental, the social, and economic sustainability of the district heating and cooling networks. So, well, in order to address this objective, we introduce the restore concept, but before, let me please set the context of this concept. It's important to mention that here in the left side, you can see different energy sources that we grouped depending on the energy that they provide. We have a first group in red color that are renewable sources that could provide heat at high temperature, like geothermal energy, high temperature geothermal energy, concentrated solar power, or high temperature from waste industrial heat. Then we have the second group in green color, technologies that provide electricity, like PV panels, but also wind energy. And finally, we have the yellow color, which include the technologies that provide heat at medium temperature, which could be, for example, the solar collectors, flat plate collectors, and low temperature geothermal or medium temperature heat from different waste heat industries. Well, on the other side, the right side, we have the users. In case of high temperature, we are talking about different industries, paper industry, food beverage industry, steel industry, cement industry. Then in green color, the consumer of electricity, that here is represented by the electrical grid. And finally, we have the consumer of mid temperature, that in our case is the district heating. So, well, nowadays exists a limitation of integration of these energy sources to provide services to these users, because there is a mismatch between, on the one hand, a mismatch in time. The production happens when there is no demand, or vice versa. And then also exists a mismatch regarding the optimum condition of operation of the energy sources and the optimum condition required by the users. So in this context, we introduce the restore technology. That's, as I said before, we consider the organic Rankine cycles and the thermochemical energy storage. And first, for charging the system, we use a heat pump that harnesses the heat at medium temperature, and also electricity for sustainable sources, and release heat at a higher level of temperature to run the thermochemical reactor that could also be fed by directly by heat at high temperature from the other sources. In this reactor is a suspended continuous reactor where we have thermal oil, but we also have a thermochemical material suspended in that oil. And here in the reactor, we provide the heat at high temperature to start a reaction that is endothermic, and we produce products, thermochemical material like product, but we also have the oil, the thermal oil at high temperature. So this energy is stored on the one hand as thermochemical storage for seasonal energy storage purposes, and as the other hand, we count on a sensible heat storage that is used for daily energy storage. When we want to discharge the system, the heat at high temperature could be used in different industry, but also through the use of an organic Rankine cycle, we produce electricity to the grid, and we also produce medium temperature heat to the district heating, all of that on demand. In some cases, it's also important to mention that the organic Rankine cycle could be used as a unique machine that is reversible and work as heat pump during the charge, and then as organic Rankine cycle when we want to discharge the system. So, well, that's about the concept, but what we plan here in our project, what are our activities? One of our main activities is the validation of this concept up to TRL4 that is a validation of the technology at lab scale, and we can distinguish two different paths in Restore. The first path is the path in charge of validating thermochemical reactor, and here we consider two different stages. The first stage that is focused on manufacture and test a small scale continuous reactor is something that has been already carried out and successfully fulfilled. And then we have the second stage where that is planning the project that is manufacturing and test a bigger scale thermochemical reactor. On the other hand, we have the reversible organic Rankine cycle path. Now we are working on manufacturing the prototype of the reversible organic Rankine cycle that will be then moved from the CENER basket facilities to the University of Milan, where it will be deep tested and validated in the polyimide thermal loop. After this first validation in Politecnico de Milano, it will be moved to the facilities on Wien and will be coupled to the reactor to finally build the Restore full prototypes, where we will carry out the final validation of the concept. In addition, other activities that we consider in this project is the analysis of the replicability of the solution. And for that, we define what we have called the virtual use cases. These virtual use cases are a virtual implementation of the project concept for specific real facilities spread over Europe, and includes activities like impact analysis through modeling and simulation, optimization of the solution, considering not only energy efficiency but also cost effectiveness. These virtual use cases also will consider the requirements imposed by the final users and also their feedback. And finally, also a characteristic to remark is that they will be publicly available in an open web-based simulation platform. Regarding these use cases that we consider in the Restore project, we plan to analyze 6 different use cases. The first one is the use case of Bronder's lead, which is focus on the use of parabolic shaft collectors and a biomass plant to provide heat to a district heating network. Then we have also the Rodolph use case, where a cement factory provides waste heat to a district heating network. In a similar way, we have the use case of Mondi, but in that case, we have a paper industry coupled to a district heating network. And we have also the Brescia use case, where we have a steel industry coupled to a district heating network. Then we have the Orkischen in Germany, which use geothermal energy to provide district heating services to a community. And finally, in a smaller scale, we have the final use case, that is the analysis of the restore solution in the Politecnico di Milano, in the campus, where PV and biomass is available. Well, concerning the implementation of this project, we consider 8 different work packages. The first one is focused on the definition of requirements and specification, but also is in charge of carry out the analysis of sustainability of the solution in different terms: environmental, social, but also economic terms. Then this work package also interacts with work package 2, that is focus on the development of the thermochemical energy storage. And we have also the work package 3, that is the work package focus on the organic cycles. We have the work package 4 in charge of the validation and testing of this technology at lab scale, and the work package 5 in charge of the virtual use cases. Then we have work package 6, 7, and 8 to cover some transversal activities, such as the exploitation and business model development, the communication and dissemination, and of course the coordination and the management of the project. So to conclude this presentation, also introduce you very briefly the consortium that will be carry out this project. We are 11 different entities spread over Europe, and CENER, the National Renewable Energy Center of Spain, will be the coordinator of this project. And then we count also with 2 Wien that are their main activities are related with the thermochemical energy storage. Politecnico de Milano, that is focused on the research on heat pumps and organic rankine cycle. And then we count with 2 companies. The first one, Turboden, that is focused on the application of these organic cycles to larger scale applications. And then Werner, which is a small company focused also in application at a small scale of these organic cycles. Then we count also with Syntec, which is in charge of the virtual use cases and the development of the virtual platform. Aalborg CSP, that are experts in the district heating and cooling sector, and also experts in they have their own technology for seasonal energy storage. Steinbach, that is divided into 2 different entities. On the one hand, Soliters, in charge of dissemination and communication, and also expert in the district heating and cooling sector. And we count also with Steinbach Innovation, that will lead the exploitation activities. Also in the consortium, we have Andreas, that provides the expertise in the paper industry, and UBB, in charge of the life cycle assessment, and finally Prospect Institute, which is dealing with the social assessment and also the stakeholders engagement activity. So that's all from my side. I hope this presentation gives you a general idea about the Restore project, and just encourage you, if you are interested, to have more information, find more information on our website and also in our social media. So thank you for your attention.
So thank you, Francisco, for this great overview about the Restore project and for explaining the concept in detail. I think we can say for sure that very decisive for the efficiency and also the economic competitiveness of the Restore technology is the performance of the thermochemical energy storage solution. And with this, I'm happy to introduce Professor Andreas Werner from the Technical University of Vienna as our next speaker. Andreas Werner is professor at the Institute for Energy Systems and Thermodynamics with great experience in coordinating research projects, and he also published many high-ranking publications on thermochemical energy storage and other energy and thermodynamics papers. I'm happy that he's here today as expert and as leader of the TCES work packages, which is responsible for manufacturing a demonstrator of a thermochemical energy storage. So I'm happy that you're here today. And the stage is yours, Andreas. You can take over screen sharing now.
Yes, many thanks to all. My name is Andreas Werner, as Thilo said. I am working at the Technical University of Vienna at the Institute of Energy Systems and Thermodynamics, and I have the pleasure to introduce you a little bit to thermochemical energy storage systems. Do you see my screen at all?
We see it, but not in presentation mode yet.
Not in presentation mode yet. Okay. Do you know where to switch? Okay.
Maybe you have to share a different screen.
Yeah, okay, I will try. It's fine now?
Now we can see it in presentation mode.
That's perfect. Many thanks. I want, first of all, to say thanks to all the PhDs and the professors who are involved in that work, which are Lena Schmieder and Günther Wedel, who are PhDs at the Institute of Process Engineering, Franz Winter, who is the responsible professor, Stefan Denner, Shonit Hassanejad, and Leisan Mukamechina, who are working at our institute, and even thanks to our to the leader of our research department, Professor Markus Haider. So first of all, let's give an overview about the topics I want to discuss with you. For a short overview about the thermochemical energy storage concept, the different thermochemical materials, some reactor types which are applicable for realizing thermochemical energy storage, a short overview about experiments to describe thermochemical materials during reaction, during charging and discharging, some remarks about the suspension reactor and why we selected it. Let's also consider some physical phenomena which are important for thermochemical storage, like heat transfer. About flow structure and modeling, I will just say some words. And last but not least, process simulation, where SimTech is strongly involved and where we were allowed to cooperate to develop models which will be used for process simulation of the combined system thermochemical storage as well as ORC and heat pump cycle for charging and discharging. So let's go further. A few words about thermochemical reaction mechanism. The picture you can see here is very old. It comes from our first days where we started to concentrate on thermochemical materials. Basically, the systems we concentrate on consider a certain solid material which to which heat is added as reaction enthalpy, and thereby another solid component is produced, and a gaseous component, in the easiest case, is released. Of course, it can also be in liquid phase, but the concept of thermochemical storage is something like that for the charging reaction. For the discharging means charging and discharging means heat input or heat output. For the discharging reaction, the produced solid matter is recontacted with the gaseous or liquid component, in our case here water again, and the original chemical compound A is produced and again. And if everything works fine, the same amount of heat in form of reaction enthalpy will be released again. In the meantime, the material can be stored in the time between storage and charge, and therefore thermochemical energy storage can be a good solution for seasonal storage. Fine. A short overview about TCS reactor systems. Basically, one, I believe, would concentrate on fixed beds, moving beds, fluidized beds. The reason why I put it into brackets, the moving beds, was that we did not work on it. Yeah, we worked on fixed bed, we worked on fluidized beds, and we worked on screw reactors. So these were typical gas solid contact systems to realize the thermochemical reaction. We concentrated on fluidized beds, and we even touched screw reactors. And in many cases, we found out that it is difficult to get sufficient contact between the gaseous phase, between the gas and the solid matter, to supply sufficient conversion of the particles. I don't say that it is not possible, but especially for the moving beds, it is of course possible, but it's necessary to select particle size and reactor adequate so that good performance can be reached. One of our very early experiments showed the typical channeling at very fine solid matter, where the gas passed by through the fixed bed or the fluidized bed, and where only insufficient contact between the gas phase and the particles occurred. So one reason, not all reasons, but one reason to select a suspension-based system can be to prevent this phenomena of agglomeration, of channeling, which is very present at fluidized beds and well known from there if cohesive powders class Geldert class C are used. On the other hand, even enhanced heat transfer behavior inside such a suspension reactor can contribute to the fact that a suspension system could be a nice solution even for TCM systems. Some remarks about the material. When we started our research on thermochemical materials, we didn't have a good overview about all materials which can be used. And the list I give to you here, which shows here the boron oxide, the calcium oxalate, the magnesium sulfate system, the calcium chloride, the potassium carbonate, and the copper sulfate. It's a very short list of all the components which would be available. When we started with research on thermochemical energy storage, we created a MATLAB-based search algorithm to identify different reaction pairs which could be used for. There exist a lot of components really applicable. The number of really applicable systems is maybe in the range of up to 100 systems, I would say. Yeah, but this is a number which can be discussed. For our restore system, we are interested in a reaction pair which is working below 220 centigrades for the TCS reactor and below 165 centigrades for coupling with the reversible OSC system. Of course, we are interested in high energy density. Who is not? And the materials we have selected can reach values in the range of about 2 gigajoules per cubic meter. Always keep in mind, this is a fraction of that what fuels, biogenic fuels, or even fossil fuels can have. So you can multiply this value with 10 or 20 if you compare it to oil or even wood. Of course, other requirements are to a high availability and a low price of the system, and of course, safety concerns and toxicity are also very important topics which have to be considered when talking about thermochemical energy storage. Look, I just can give you a broad overview about the things we are doing, but it might give the impression that thermochemical storage and development of reactor systems is a very widespread field of research. Of course, you have to consider and to describe the reaction behavior of the system. The question can be, how fast does the reaction take place, as well the charge and the discharge reaction, and how stable are the system. Is the system dependent on the number of runs? How is the cycle stability of the material when it has been used one time, a second time, a third time, and so on? Another question, of course, is what is the optimum pressure where the reaction should take place? Lower pressure influences the charging and discharging temperature. For discharging, it could be helpful to increase the pressure due to chemical equilibrium conditions. By changing the pressure, you can influence the level of heat release and heat input, represented by the equilibrium condition for the system. Of course, you have, since we are working with a suspension, you have to consider that the salt hydrates, as I showed you before, they are hygroscopic. So if you store them within a tank, you have to take care for that they can't absorb moisture from the ambient. Otherwise, reaction would take place during the storage period, which is greatly unwished, because then you would convert it during storage, and this must be prevented. And therefore, we did tests how much oil is necessary, not only in the reactor, but even in the storage tank to protect the material from being hydrated by ambient air. Therefore, we did some experiments, and some results about that are given here. So our conclusion was that around 38% of oil helps in this tank to prevent the material from getting hydrated. Of course, you have to consider the chemical off aspects of the storage material. I am very thankful for all the comments of our colleagues when discussing handling, transporting, storing the material, to keep our eyes opened for several problems or issues which could happen to health of people who have to work with the system or who are living around. If you look to the reactor, you have to concentrate on how behaves the suspension in the system. Do you observe foam generation? How is the global kinetics of the reaction for charging and discharging, as I mentioned before? Is it too slow? Is it fast enough to be applied to a real reaction system? How does the system behave in relation to agglomeration? How is the cycle stability, as I mentioned before? And how is the corrosion behavior of the salts? For instance, think about the calcium chloride, which could cause corrosion on the metallic reactor walls. So certain materials have to be selected to cope with. Fine. So these were some remarks about the solid materials, the thermochemical pairs which can be used. Now I want to give you short an impression of the reactor system which is necessary to be operated. For charging and discharging, the core component itself is, of course, the reactor. It's a continuously operated steered tank reactor with a heat exchanger coil inside and with a multi-stage steerer to distribute the suspension, the oil, and the thermochemical material as well distributed as possible. The compounds themselves have to be stored in separated tanks outside, one tank for the oil, one tank for the thermochemical material, certainly covered with a little amount of oil, as I mentioned before. So in the case of charging, the oil and the suspension are preheated and suspended and mixed, so suspended and transported to the reactor. Heat from the heat pump will be transferred via the heat exchanger surface to the suspension, and therefore the charging reaction, releasing in our case gaseous water, will take place. The water is condensed and collected for further application in a certain tank. The dehydrated material itself is extracted from the reactor. Oil and salt are separated. The oil is retransported to the oil storage tank, and the dehydrated salt, of course, now has to be stored in another storage tank. So this was in detail, or more or less in detail, the charging reaction. The discharging reaction, where the heat is released again, is shown in this picture. The system is now operated in the opposite direction. dehydrated material is added to the reactor. Water in liquid form is even added to the system and distributed in the oil, and the solid matter heat is released again and transferred via the heat exchanger surface now to the overseas cycle where electric heat can be generated. The hydrated material itself then is collected again for the next use in the red indicated, with red labels indicated materials tank. This is this is an impression of our very first continuously operated TCS system, our continuous stirred tank reactor. The main components to be used are a feeding system for the suspension, the stirred tank to enable the thermochemical reaction, independently on the question whether it is the charging or the discharging reaction. We need a recirculation pump for the oil, an extraction system which, as I showed before, separates the oil from the solids, and of course a control system for the whole system. I wanted to show you some video about that, but it repeatedly helped to collapse the presentation, so I put it out. We had to cope with certain issues. One of the main issues happened during the experiments was the foam formation, therefore different possibilities to prevent. Compare the left and the right picture, where on the left-hand side, you can observe very serious foam generation during the mixing and reaction stage with adequate measures. For instance, by adding some silicone oil to the mineral oil, which we usually use to create the suspension, can help to prevent foaming. As an alternative, of course, even some mechanical foam destruction concepts exist where we tried to evaluate, but we didn't work out in detail. What you can see here is some overview about the different types of reactors we intend to work on. This is the so-called intermediate steel suspension reactor, which consists of more or less the same components as I talked to you before: a TCS storage system for the oil and the suspension, a preheater system, a system where water can be collected and even re-injected to the system, the TCS reactor itself, the separator for the suspension to separate the oil from the thermochemical material, of course a heat supply system, and therefore a possibility to observe the reaction in a continuously stirred system at ambient and enhanced pressure. The next bigger step of investigation will concentrate on the so-called prototype dual-purpose reactor. This is the next big reactor we intend to build in our laboratory, and to this system the reversible ORC will be connected to. So some values about it will have a thermal power for charging of 30 kilowatts. It will be installed to our laboratory. We will realize a mean logarithmic temperature difference of about 10 kelvins at an operating temperature level of around 120 centigrades in the system. The design values for the vessel will be 135 centigrades and 4 bars operating pressure. What are we concentrating on? We want to be able to formulate and check and prove the heat balance for the system. We will try to validate our CFD simulations concerning flow distribution and suspension distribution along the heat exchanger surfaces and in the inner of the reactor. And of course, one of the major questions to be asked is, at the very late phase of the project, we will couple it to the reversible heat pump oversea system. So some process flow diagram for the 30 kilowatts reactor. We even need a thermochemical energy the storage system, even a preheater system, which will be especially developed for that larger type of reactor. In the intermediate steel reactor with a 5 kilowatts power, we will use a steered tank for preheating. We even need a water section for water injection for the discharging reaction, the thermochemical reactor itself, the suspension separator to separate solids from the oil. Some other types or some other field of research which are in close connection to the development of the system is of course the question, how is heat transfer behavior in the system itself? What you see here are very, very preliminary experiments from the very beginning of our project. We had a jacket heated reactor with no coil inside. We just tried to find out how quickly does a suspension with a certain concentration of solid matter heat up inside the reactor dependent on time. It was a batch reactor, so no continuous reaction at this point or at this stage of experiments. And we varied the mass fraction of solid matter from 20 to 30% because this is about the value we want to realize in our thermochemical system. Of course, this is the reason why you can see a very simple types of stirrers here. We also wanted to find out what effect on heat transfer behavior dependent on shape and type of stirrer used. In the next step, we we developed a continuously operating system with a heat exchanger, with a coiled heat exchanger inside the reactor, which is similar to that which will be realized in the 30 kilowatt thermal reactor. We selected different types of solids concentration, and we made experiments with different types of with different rotational speed of the system. Yeah, here you can see some impressions about our very first about the experiments with that coiled system. The difference is that we have here already a coil inside in comparison to the very first experiments with the jacketed wall reactor. And finally, we identified the level of heat transfer coefficients from the suspension to the coil, which was in the most cases up till now in the range of 600 watts per square meter in Kelvin. we found a slight dependency on the solid concentration at different rotational speed of the stirrer, which was varied from the 500 to the 700 rounds per minute. So you can observe here a slight dependence on solid concentration as well on rotational speed of the stirrer. Stirrer design and design of the reactor so that inhomogeneous distribution of solid matter is prevented is one of the main topics of our experiment, of our simulation, and so different CFD simulations covering that field are performed. We have now in our lab, there is some impression about that, and other type of continuous stirred tank reactor, where we now are doing heat transfer experiments under continuous operation, even by observing the mixing behavior of the suspension in the system when it's introduced to it and extracted from. Fine. So finally, I want to talk a little bit about our simulation work. The thing you can see here is it concerns the IPSE Pro simulation of the TCS system combined to the ORC cycle. These models are implemented to the IPSE Go platform, which is being developed within this project in close cooperation to Simtech, which is a very fruitful and interesting topic. And the IPSE Go system is a web-based platform to do simulations of such type of energy storage systems online. And by covering or by simulating the use cases which were shown by Francisco at the introduction, different stakeholders are invited to try out this system for different applications or for their application. So on the left-hand side, green colored, you can see the thermochemical storage system modeled with the reactor itself. In case of charging, we have the heat input to the system from the heat pump system, which is indicated here with the compressor, with the condenser. In that case, the heat exchanger surface in the suspension reactor acts as a condenser, and therefore we can operate and charge our thermochemical material, which is fed to the system, which is preheated here, and which is mixed with the suspension here. So the both main components, thermochemical energy storage system and heat pump, well indicated here. We have developed together with Simtech a library which contains the property data for the thermochemical material from the table I showed you before. So you can see here the CO2, the COSO4, and the copper sulfate, the hydrate compound, which is fed to the system, which is mixed with the thermal oil, which is preheated, and then fed to the charging reactor. Leaving the system, it has to be cooled down again. Here you can see, just for indication, a heat transfer fluid, which is used to cool down and to preheat the entering system again. Further heat integration, of course, is necessary. Even the vaporized water has to be condensed, and process heat and integration has to take place to reach sufficient efficiencies. As necessary in process simulation, we can define mass and energy balance to evaluate the process and to evaluate the quality of heat integration. We can operate it in combination for charging and discharging. This simple scheme should show. We also simulated the discharging system. We have on the left side again the thermochemical storage system. On the right side, instead of the heat pump, of course, now the ORC system. At the ORC system, the heat exchanger inside the thermochemical reactor now is working as an evaporator with the target to evaporate the working medium of the ORC cycle to be expanded in the used screw expander. Indicate here on that picture, you can now you can see again the major components of our TCS system. In the opposite to the charging mode, we now add water in liquid form. In liquid form because only in that form it can be used within the thermochemical reactor to release the heat, which, as I mentioned before, is necessary for the operation mode, for operating the evaporator and for operating the ORC cycle. Now, we currently solve mass and energy balance to observe the main operating parameters of the system, which are also indicated here. Now, even the scheme for the whole system. And so with all of that, I am already more or less at the end of my contribution, with which I wanted to give you an overview about the different types of research work we are doing together in our group. So the next step, which will be done in our reactor, will be the implementation of the 30 kilowatts reactor, which has to be tested in our lab. The first step of it is to test the storage system alone without combining it with the heat pump ORC system. And in the second step, the very late stage of our project, the heat pump ORC system will be transported to our lab after testing it in Milan, and then it will be connected to the storage device in our system. Another important point is the use of the IPSE-Pro and IPSE-Go models. The IPSE-Go model for the web-based system to analyze the replicability of the concept to different application cases, especially to the different use cases which were shown by Francisco before. So, dear all, I am now at the end of my contribution. Many thanks for your interest. Let's have a nice discussion after. Thank you.
So thank you, Andreas, for this great presentation about the fundamentals of thermochemical energy storages, and also for giving insights about what's happening in the labs of TU Wien. And I think that it's already a great success that you have tested various thermochemical materials under different conditions, and also the manufacture and the operation of a small-scale continuous reactor. It's a great success. Also the work with the simulation in IPSIGO, and I'm excited at what's happening next with the upscaling. So yeah, with this we have a 10 minutes break now, coffee break. I want to remind you that the Q&A feed is open for your questions, so you can use the break time to post some questions, and of course also to get something to drink. So enjoy your coffee or tea, and we will be back here in 10 minutes. Hello and welcome back. I hope you enjoyed your break, and we are now going to hear the last presentation of today's webinar, which is about the reversible organic Rankine cycle as second key innovative technologies applied in the restore concept. We have Marco Astolfi and Dario Alfani here from the Energy Engineering Department of Politecnico di Milano. They are both carrying a Ph.D. degree and are experts in non-conventional thermodynamic cycles, multi-energy system optimization, and low-carbon technologies. I'm glad that you're here today, and the stage is yours. Marco and Dario can start screen sharing.
Thanks, Tito, for your kind introduction. I'm now sharing the screen. Let me know if you can see the presentation in presentation mode.
Now we can see it in presentation mode. Perfect.
Perfect. Okay. Thanks. So welcome everybody. This second presentation will be focused on pumped thermal energy storage, and also carbon batteries, based on reversible organic Rankine cycles. We will start with an introduction, then we would have some, topic more, on the fundamentals of this technology, and then some more numerical activities we carried out for the Restore project, both focused on a system for seasonal storage and another one more based on daily cycling. The motivation in why using energy storage have been already explained by Francisco at the beginning of this webinar. But the main point is that basically all the energy grids in developed countries are today more and more penetrated by renewable energies. And the non-predictability and non-dispatchability of variable renewable energy sources like wind and solar, especially photovoltaic, is already posing some difficulties in operating the grids. This would be solved by the availability of energy storage solution for both daily base storage in order to catch the price variability and gather remuneration by using off-peak electricity at low cost during periods of high production from renewables, and then get high revenues in periods of high price of electricity when renewables are reducing their impact on the grids, and thermal power plants are rising up. And this is basically a kind of operation that is oriented to a daily cycling, and so between 4 and 10 hours of equivalent capacity. However, there are also many countries around the world, especially in China, California, but also South of Europe recently, that are facing huge renewables curtailment during the year. Especially, this is the chart for CAISO TSO in California, where it's possible to see the pattern in 1,000 of megawatt hours which are curtailed from solar and wind energy. And this poses some limit also in having a daily storage system because of the highest impact of solar energy, but also wind energy in certain months of the year. And for this case, energy storage would then solve the problem on seasonal based by limiting curtailment of renewable and promoting the decarbonization of power production. If we look then in a future scenario where the penetration of renewable energy will go above what is currently the status, so around 40, 60 in most virtuous countries, we will see that the amount of hours rated power for the storage is increasing exponentially, this is a logarithmic scale, by increasing the share of renewables, solar and wind, on regional grid. And this also shows that long duration, so above 8 hours, but even longer for monthly and seasonal storage, is something that will be mandatory in the soon future in order to decarbonize electrical production. Considering the technologies available today, they can be basically split in 3 main groups. We have flywheels for a very short capacity and very short discharge time, electrochemical batteries, which is a huge class of technologies, but all of them are characterized by degradation over time, a rather short lifetime because of aging and wearing issues, and then also a little module capacity and a power to capacity ratio, which is between 1 and 4, so it's not possible to decoupling the power and the capacity of those systems. And finally, there is a pumped hydro energy storage for a large storage capacity, a longer duration. The perception is that the batteries are super important in energy storage facility, but actually 94.5% of the energy storage in the world is based on pumped hydro. However, pumped hydro has reached the limit in many countries because the need of specific orography of the soil, and also the problem related sometimes to visual impact and impact on ecosystems. So what the market needs today, and this is also one of the questions that Restore project would like to answer, is that there is a large need of technologies that will be able to provide energy dispatchability, at least on daily based, but also towards long duration energy storage and seasonal period, while being affordable, safe, and efficient. Among those, there are 2 main groups of technologies. For a super long seasonal monthly storage, we have mainly, let's say, chemical storage, so production of fuels from synthesis and or hydrogen, so methanol, dimethylator, ammonia, and other synthetic fuels. On the contrary, more on daily and weekly storage, mechanical and thermomechanical energy storage can really play a role. The idea of Restore is a bit combining both technologies, since the energy storage itself, as you saw in the previous presentation, is provided by a thermochemical energy storage, so with high energy densities and the possibility to store heat as a solid, so with an inexpensive equipment. And on the other side, also integrate this thermochemical energy storage with a thermomechanical energy storage based on carbon batteries. Carbon batteries are a wide topic of research, and the basic principle is that in carbon batteries, the electrical energy is stored in form of heat. And during the charging process, electricity can be directly dissipated as heat, or more efficiently, it can be used by an heat pump to exploit the heat available from the environment, from a cold storage, or from waste heat, in order then to store thermal energy at higher temperature. During discharge, the system is basically reverted, and to produce back power is required a power cycle that would operate between the thermal energy storage and the environment or the cold storage. Even more intricate system could be, let's say, planned using architectures that would integrate an additional heat pump level at low temperature, so below ambient temperature, for example, integration in district cooling during charging phase, and then the possibility to exploit the heat released from the power cycle for heating purposes, so with integration with district heating. The same concept of carbon batteries can be also reverted below the ambient temperature, and so playing just with a cold storage rather than using a high temperature storage. But this is an idea which is investigated in general in literature, but it's not something the research project is focusing on, because we are basically playing with the thermochemical energy storage at temperature higher the ambient one. Regarding carbon batteries, there are several options depending on the thermodynamic cycles and the type of thermal energy storage adopted. Regarding thermodynamic cycles, there are different solutions like a reversed closed Brayton cycle, transcritical supercritical CO2, steam Rankine cycles, and organic Rankine cycle. While on the other side, regarding thermal energy storage, we may have the store of heat as in a variable temperature heat storage, so with a heat transfer fluid and, for example, a 2-tank storage or a packed bed thermocline vessel, or isothermal heat storage that could be a phase change material, but also, as in the Restore project, a thermochemical energy storage system. Just to give a brief overview of those systems, reverse closed gas Brayton cycles have a, let's say, company of reference, which is Malta in the United States. They use a reverse air Brayton cycle. In red, there is the charging phase, and in blue, the discharging one, that is operated with air between a temperature of -70 Celsius, storing in cold methanol or other organic fluid, and producing heat at high temperature, which is stored in molten salt. Inevitably, the temperature variation in the heat input and heat release processes require the use of variable temperature heat storage. Transcritical supercritical CO2 mainly refer to the technologies that are developed by Ecogen in the United States and MAN Energy Solution in Europe. They use a transcritical CO2 cycle that basically adopts an isothermal temp heat storage, so a phase change material at low temperature, while they accumulate heat under variable temperature for the high temperature side of storage. The system are now in, say, pilot scale phase, and they will be able to reach a rather good efficiency around 55–65%. Then there are systems based on Rankine cycle, and depending on the fluid, so steam or an organic fluid, they belong to different categories. Steam Rankine cycles are very complex in the design because of the need of intercooled compression process, while for organic Rankine cycle that are adopted in this case, the possibility to exploit the overhanging saturation line of the fluid allows also to limit the maximum temperature of the fluid after the compression. Especially in this case, using organic cycle, the heat input and the heat release from both the heat pump cycle and the power cycle are basically a phase transition process, so evaporation and condensation. And so the matching with the isothermal heat storage is particularly interesting. In this case, it's possible to use phase change materials. There are many of them based on fatty acids, but also inorganic materials in phase change at different temperature levels. But they also pose some limits in terms of a transfer coefficient and energy densities. While in this case, thermochemical energy storage is investigated for increasing the compactness of the system and the techno-economical viability. Regarding the performance, basically the carbon batteries are based also on a heat pump cycle and a power cycle. And from a theoretical point of view, so while considering an ideal cycle, the round-trip efficiency, which is basically the energy you can get from the system with respect to the energy which is consumed by the compressor of the heat pump, is basically the product between the coefficient of performance of the heat pump and the efficiency of the power cycle. In case of an ideal system, independently of the temperature of the environment and the heat storage, the efficiency can be always is always 100%. However, when considering a reasonable second law efficiency of the heat pump and the power cycle, so considering real components with pressure drops, with turbo machinery having a realistic efficiency, then the maximum round-trip efficiency when considering just an isothermal heat storage drops below around 40%. And this efficiency can be even lower if temperature difference due to heat transfer requirements are applied in both charging at low temperature and high temperature storage. So is tricky with just an isothermal heat storage as a thermochemical reactor to go above 40% of round-trip efficiency. However, this performance can be strongly increased by exploiting some waste heat as heat input for the heat pump. So the availability of waste heat allows to increase the coefficient of performance for the heat pump, thus boosting the round-trip efficiency of the system that in theory can also reach values above 100%. So with the possibility to get more power, more electrical energy than the one that was used during the charging phase. In this case, it's possible to see some more realistic results, which is the performance of the system in terms of round-trip efficiency by varying the storage temperature and the waste heat recovery minimum temperature. And is that so possible to see that with a storage at around 130, as we are proposing for the restore system, and exploiting a heat available from waste heat at around 80 Celsius, would be possible to push the round-trip efficiency of the system up to 100% if everything is, let's say, sufficiently high in efficiency in terms of turbo machinery and this is much better from a theory point of view with respect of using a sensible heat energy storage, so accumulating a heat in a variable temperature heat transfer fluid, which vary its temperature during charging by heating up with the heat released from the condensation of the fluid, and then cools down in discharging phase by releasing heat to the power cycle. In this case, the higher is the variation of temperature, the lower is the maximum performance of the system. And so going towards a sensible thermal storage would also then penalize the performance. This is the reason why Restore project is focusing on isothermal energy storage based on thermochemical energy storage and organic Rankine cycle. Regarding organic Rankine cycle, the name organic means they are using not water as a working fluid, but they're using a proper organic fluid, so a molecule that contains carbon and hydrogen atoms, of course, and so all the hydrocarbons, so alkanes and other, let's say, cycling or branched hydrocarbons, but also refrigerants fluids. The availability of fluids is very large, has been already investigated in many applications from low temperature up to high temperature. And the advantage in this case is that depending on the temperature of the waste heat and the temperature of the reactor, and so the maximum temperature of the system, it's always possible to identify a working fluid which has the correct critical temperature, so the correct thermodynamic condition properties for boosting and maximizing the performance of the system. Some of them are flammable, some other ones may be more impactful from global warming potential when released. Some others may have some problem related to very low condensating pressures and very high volume flow rate of the fluid, but the possibility of selecting them in a wide range keep always the possibility to get the best trade-off between system cost and performance. Regarding organic cycles, if you have some curiosity and if you're not expert of this, you will find a map online, which is very easy to find, is a world map, Organic Rankine Cycle, that has been built tracking the references of more than 35 Organic Rankine Cycle manufacturers, and now list more than 3,000 plants with an overall installed capacity of 5 gigawatt-hour. You can scroll and zoom and see how many plants have been installed in 4 main applications, which is solar, waste heat recovery, biomass, and geothermal energy. Going back to the thermodynamics, this is the basic concept we are investigating in Restore system. So it's a system which charges with a heat pump cycle, so a reversed Rankine cycle, and then run a power plant, a power cycle in still in a saturated, nearly saturated condition. 3 kinds of systems are now under investigation in the Restore. The first one is the fully reversible system, where basically all the components are reversible. So we use the same heat exchanger and the same machines in both operating modes, in both charging and discharging. In this case, only volumetric machines can be adopted because they are reversible by nature, differently from turbo machineries. and only one working fluid can be selected. So you need to select the best working fluid to be used in both cycles. The advantages are related to the minimum capex, so lowest investment cost, which is also important for a system that is not operating the full year likely, and so depending on the number of cycles and the time, the hour of storage will have a capacity factors that are not closer to unit for sure. Another advantage is related to the compactness of the system and the simple layout. The drawbacks are more related to the machine efficiency that cannot be expected to be very high because the same volumetric machine like a screw or a scroll expander is used in both operations, so the performance cannot be maximized for both operating mode. The heat exchanger would require an high operability, high flexibility in the operation because they need to move to different pressures, and so they need to be flexible in handling the fluid. And our system that can be used for a small scale, so below 500 kilowatt. And of course, another disadvantage is that you can select only one fluid for both modes that would maybe sometimes limit also the performance of the system. Then we are also investigating coupled cycles that are more indicated for larger size application or in all those cases where it's not possible to operate a reversible compressor expander. In this case, the proposal is to use different machines, so a separate volumetric or a turbo machinery, so a separate compressor and expander, but using the same heat exchangers. Also in this case, a single fluid can be adopted. The advantages are that the capex is not increasing a lot because in any case we are talking about low efficiency system, or at least high heat to power system, and so the cost of the heat exchanger has the largest share in the breakdown of capital investment. So adding one or two turbo machinery is not making a big difference for this kind of system, so the capex stay rather low. The compactness of the system is not limited by this. The layout is still rather simple. It's just a matter of adding some three-way valves in order to exclude one machine or the other, varying the operating mode. And it's possible to get the maximum efficiency from both the compressor and expander, since they are designed to operate in a specific condition. Regarding the size range, so the power output or the power input, there is no a limit for a small scale system. Volumetric machine will be used for a large scale one, as for organic Rankine cycle, large scale heat pumps. Turbo machinery is based on radial or axial stages configuration will be adopted. The disadvantages are still the ones we saw before. So the heat exchanger must be capable to operate in both operating mode, which means that the high pressure heat exchanger should operate as a condenser when the cycle is operating as an heat pump, as an evaporator when discharging, and the opposite for the low pressure heat exchanger. And this does limit only the possibility to use the working fluid into the pipes of the heat exchanger, and so with some limitation also in the type of equipment you can adopt. Finally, regarding the coupled cycles are the system with the highest degree of freedom in the design, because you simply design two cycles, so one heat pump cycle and a discharging cycle based on Organic Rankine Cycle. But so you can maybe increase the efficiency. You can also select two different fluids, but the main problem is that you are duplicating the effort in both size, dimension, but also investment cost. From preliminary calculation, these cycles are not of real interest, because the disadvantages of duplicating the capex is never paid back by the increase in efficiency you can actually get. In conclusion, Restore System will focus on reversible cycles and coupled cycles. Regarding the fully reversible cycle, this task will be handled by Enerbasque in Spain. They are a manufacturer of small-scale organic Rankine cycle, and they will focus on the design of small-scale system below 500 kilowatt from numerical point of view, but they are also going to design and manufacturing a few kilowatt, 5-10 kilowatt reversible organic Rankine cycle that is now under, let's say, construction in Spain, in Enerbasque facilities, and then it will be shipped by the beginning of this summer, end of this summer at Polimi Labs, where we will carry out a fully testing for the performance validation, and then it will be shipped again to Wien labs for the integration with the thermochemical energy storage. Regarding coupled cycles, so using two different machines for the compression and expansion, this task will be faced by Turboden, which is one of the main players in the organic Rankine cycle market at world level, which is based in Italy, in Brescia, close to Milano. And they will focus more on numerical activities, designing a large-scale system for our selected use case based on pulp, cement, pulp and paper, cement, geothermal, biomass, solar and steel production. So regarding coupled cycles, this is the basic scheme. So same recuperator, same low pressure heat exchanger, same high temperature heat exchanger, but two different turbo machinery, a compressor in a heat pump mode, a turbine in a power cycle discharging mode, and a system for the throttling of the system during charging, and the pumping station for the running as a power unit. The numerical study of this kind of system is a bit more intricate than simple thermodynamics, because the design of the heat exchanger in one operating mode would then affect in off design the operation and the performance of the discharging mode. And thus a correct evaluation of the performance and also the understanding of the trade-off between performance and cost must be faced with a specific numerical tool that have been developed during this project by Politecnico in Milano. Okay, so now I will leave the presentation to my colleague Dario Alfani, who is a postdoc here in Politecnico in Milano, a research fellow, and is the main owner of all the numerical tools for the study of this kind of technology. We'll present you some numerical activities that are also available online in a published paper about some studies on both a more seasonal based system and a daily cycling case. Okay, Dario,
thank you, Mark.
The floor is yours.
Okay. So, as Marco was saying, the numerical modelization of this kind of system is more complex when you consider a coupled system. So considering at least the same heat exchanger for both the charge and the discharge cycle. This is the flow chart on how these two systems should work when you're considering just a separate system. So a separate heat pump with each heat exchanger and the ORC cycle which have dedicated heat exchanger. So the flow chart is quite, let's say, here it seems tricky and complicated, but it's quite flawless. You design the heat pump, you design the ORC as they are, and then you combine the coefficient of performance of the heat pump with the efficiency of the ORC in order to compute your round trip efficiency. A lot of times you can see in literature that they're using this method also to compute coupled cycles. So they're assuming the behavior of the heat exchanger for the organic rankine cycle or for the heat pump, and they are neglecting the off-design performances of this heat exchanger when passing from one mode to the other. So this is definitely not the optimal way to proceed. A more correct and appropriate way to proceed would be to choose one simulation mode, so the heat pump charge or the ORC, in order to design the heat exchangers, and then to compute the performances of the other simulation mode. So if you choose the charge for the design, you're going to compute the discharge, fixing the heat exchanger surfaces from that specific process. So in this case, we decided to choose the heat pump as a reference for the design of the heat exchanger. We designed the heat pump cycle and then decided the size of the heat exchanger depending on the pressure drops, the pinch point temperature difference, and some, let's say, component parameters definition. Then we use the surface that we computed in order to simulate the organic rankine cycle by an iterative procedure, so guessing the temperatures inside the organic rankine cycle and then computing the transfer surfaces until they reach a convergence on the one they computed with the heat pump cycle. So there is this coupling between the two cycles. The tool that we have developed is quite well described in the papers that Marco was citing, and is based on a code that we've developed mostly in Python and using RefLop V10 for the computation of the fluid thermodynamic properties, so for the working fluid. In this case, we are going to propose our last work dedicated to this topic. So we decided to focus on two different case studies, one for a daily and weekly cycle, so a smaller system based on a latent thermal energy storage, a PCM, that doesn't need huge insulation in this case because the cycles are just daily or weekly. And a second system based on a cogenerative solution when we also want to dispatch a large amount of heat for district heating through the ORC condensation. So the ORC temperature is going to be higher in order to allow the dispatch of this heat for a district heating network present around the system. Obviously, even in this case, as this secondary let's say this district heating dispatching can be achieved even just with the thermal energy storage without the ORC, we're going to focus on the dispatchability of electricity as a byproduct, but still being the main focus of the work. In this case, the technology is the one that we are interested in the Restore project, so a thermochemical energy storage, even if we did not rely on the latest result produced by Wien, as this work was done actually last year. So a couple of assumptions we are considering here: quite large stored thermal power, around 1 megawatt, and a strong assumption is based on the number of charging hours and discharging hours. Obviously, in the case of coupled cycle, this assumption is particularly important because we are going to share heat exchangers. But in the case you are going to deal with the coupled cycle, you can also completely decouple the number of charging hours, so having maybe a small system that is charging a lot of hours during the day, and having just a peaker kind of plant that is discharging only a few hours per day with a higher power. In this case, having a coupled cycle, having the same heat exchangers to be shared between the heat pump and the organic rankine cycle, we decide to assume that the number of charging hours will be equal to the number of discharging hours. We assume the availability of a waste heat available for the heat pump at a temperature between 180 degrees. So we decided to cool down this in order to achieve the working fluid evaporation. And then we assume the condensation temperature based on the two different cycles. So in the case of an electricity-only system, we assumed water cooling with a temperature between 20 and 25 degrees for the coolant available, while for a cogenerative system, we assume that the district heating was a new generation kind of district heating, working with a supply temperature around 60 degrees and a return temperature around 35. In this case, the figure of merit that we want to optimize are mainly two. One is focused on the thermodynamic performance of the cycle, which is the round trip efficiency, so the product between the coefficient of performance of the heat pump and the efficiency of our power cycle, which in this case obviously is our organic rankine cycle. Differently, not having actually a precise set of cost correlation in order to assess the investment cost for this kind of system, we decide to use as a sort of proxy for what is the total cost of the system, the overall heat transfer surface computed as the sum of the high pressure heat exchanger, low pressure heat exchanger, and the recuperator, which is used in the system in order to increase efficiency. We achieved the computation of the transfer surfaces in a precise way by discretizing on the enthalpy exchange each heat exchanger. So each heat transfer area is computed as the sum of smaller segments of the heat exchanger, in which we compute the heat transfer correlation through heat transfer correlation, the heat transfer coefficient, and the pressure drops. And all these correlations have been retrieved from literature studies, from previous literature studies. The objective, the final objective for us, was to investigate the trade-off between these two figures. Obviously, if I'm going to increase the transfer surface, I'm going to decrease the reversibilities in the transfer processes, but at the same time, I'm going to increase the cost of the heat exchanger. So we want to understand which parameters are most influencing the trade-off between these two figures of merit, and how these two figures of merit are changing depending on the working fluid assumed. For the heat exchanger, we were saying that we are using discretized model for the main heat exchanger working with the reactor. We used, as we said, a stirred reactor with coil tubes inside, where the working fluid is fed from the bottom. In the case is an evaporator mode, or from the top if we're using in condenser mode, while in the case of the phase change material, so for the electricity only case, we use a simplified version of a finite tube heat exchanger, where the tubes where the working fluid is flowing inserted in a matrix of phase change material. You can see here some of the parameters that we use in order to simulate the coil tubes and the finite tube heat exchanger. And the correlation that we used are the classical one for phase transition, so the Cavallini in the case of condensation, and the Lewin-Wheaton in the case of evaporation. For the external heat transfer coefficient, we did not have the latest results from Wien, so we assumed the literature value, which is definitely higher from what Wien has obtained in its last experimental results. But still, here we are talking about a numerical study where we are considering a 1 megawatt site, so definitely a more commercial kind of system. Then we let's say we model the low pressure heat exchanger as a simple shell and tube heat exchanger, which have water in both cases flowing inside, and the tube side where we have the working fluid. This is used as an evaporator in heat pump mode and as a condenser in the discharging mode. Here the correlation are pretty simple, and all the parameters used for the heat exchanger are the one taken from just taken from it. Very similar is the recuperator. Is just the design of a recuperator from an organic Rankine cycle. So we based on a commercial situation where we have the low pressure inside the fins and the high pressure inside the tubes. As we were mentioning, we got several possibilities as the working fluid. We listed here the working fluid study in the preliminary analysis by a range of critical temperature. So we are having just critical temperature just slightly above the temperature of the thermal storage, while we can have a critical temperature way higher than the one of the thermal storage. So what we wanted to investigate is how this parameter is going to affect the final results in terms of performance and cost for this kind of systems. We decide to neglect completely fluids with GWP, so global warming potential above a certain threshold, and we try to focus with fluid that will be useful in kind of industrial application and so on, so with health, flammability, and all these kind of parameters which can be considered quite limited. Obviously, if you consider all these parameters together, the selection of the optimal fluid becomes really just on a couple of fluids. If you can relax one of these constraints a little, the pool of available candidate working fluid can be a little high. So we performed firstly a preliminary analysis just from a thermodynamic perspective in order to compute the round-trip efficiency of the fluid. And it is possible to notice that while the power cycle efficiency is quite constant, around a value of 10% for what regards the assumptions of this analysis that we published for ASME Turbo Expo, the strong change in performance of the system is given by the coefficient of performance of the heat pump. And the higher the fluid critical temperature, the higher the performance of our heat pump. On the other hand, as we were saying, also the cost of the heat exchanger is escalating. On this yellow bar, you can see the total surface of the heat exchanger. Here you have its axis, and having solution which performs better with a higher efficiency also implies a higher cost of the heat exchanger and a higher surface of the heat exchanger. Trying to understand the trade-off between these two figures of merit, we introduce this parameter, so a ratio between the round-trip efficiency and the total heat transfer surface, noticing that it's increasing below a certain fluid critical temperature, it reaches a maximum and then starts to decrease. We decide so to focus the next analysis on the fluid that, at least from this kind of parameter, was actually the most promising one, so cyclopentane, an hydrocarbon, which actually have a critical temperature which is not too high and not too low with respect to the candidate working fluid that we considered. In order then to have some parameters in order to compare this fluid, we also decide to perform a more in-depth analysis, also consider a more performing fluid, so octane, which also lead to a higher overall transfer surface of our heat exchanger, and on NOVEC 649. And this was done because NOVEC 649 was selected due to its low flammability and good environmental properties for the experimental results that will be led by Werner here at the facility of Polimi and in Turin. So the methodology was based on a genetic algorithm, changing the optimization parameter between two ranges. The most important optimization parameters that we decide to change are the one that are referring in order to size the heat exchanger, so the pinch point temperature difference of the main two heat exchanger of the cycle, so the heat recovery evaporator and the condenser of the heat pump. You can obviously notice that the lower they're going to be, the higher is going to be the surface of the heat exchanger, but also the lower the cycle performances, while the one of the recuperator is not be set because it's a value which is computed in order to fix the compressor outlet temperature to a value that we want to achieve. So at the end of the recuperator, we need to have a compressor inlet temperature able to reach the compressor outlet temperature that we are targeting. The second set of optimization parameters are the pressure drops, which are varied in relative term between 1% of the inlet pressure and 20% of the inlet pressure, so a huge pressure drop. And in this case, the higher the pressure drop is going to be, also the higher the transfer coefficient, because the fluid is flowing more, let's say, faster inside the tubes, inside the heat exchanger. And so also the lower the area of the heat exchanger due to the fact that we have a higher heat transfer coefficient. Also, the higher pressure drop is going to lead to a lower system performance due to the higher compression ratio required in charging and the reduced expansion ratio available at the turbine for the discharging. So we have for both figures, for both the pinch point temperature difference and the pressure drops, some trade-off. Regarding instead the turbo machinery, we consider a fixed efficiency for both the pump, the turbine, and the compressor. So the compressor we set 80%, the turbine 85%, and the pump 75%. Obviously, a more sophisticated analysis would include the effect of the working fluid operating parameters and the working fluid selection on the turbo machinery performance, but this was beyond the scope of our analysis. So I'm going to briefly present the results of this Pareto front analysis. You can see on the right the overall transfer surface against the round trip efficiency is the first two plot for the electricity only case and the cogenerative case. In blue dots, all the population investigated is highlighted, while the Pareto front of optimal cases is reported in red. It's possible to notice that with an electricity-only solution, we can achieve practically 10% point more on the round-trip efficiency, passing from a maximum of around 60% to a maximum of 50% for cogenerative cases. And this is due mainly to the increase in the condensation pressure, so the decrease of the performance of the organic Rankine cycle in the cogenerative case. In the second set of plots, we depicted the trend of the overall surface ratio to the RPE, so the point that we were trying to optimize in the previous work. And we can notice that pushing the solutions to the maximum round-trip efficiency is not always beneficial from the trade-off between these two figures. So this case is a sort of specific round-trip efficiency to the surface area of the heat exchanger, and the trend of these two figures highlight the fact that it's not always so beneficial to push to the maximum performance due to the escalation of the cost of the heat exchanger and the size of the heat exchanger. So this was, I was trying to highlight the fact that the maximum is actually not for the maximum performance, the maximum piece ratio. Then we selected, this was the analysis that we did for cyclopentane. We selected a couple of variables that we wanted to highlight the trend. It is possible to notice that obviously the higher the pinch point temperature difference, the lower is going to be the performance of this kind of system, but also the lower is going to be the total surface. And these are only the variable from the Pareto plots, from the optimal points of the system. And it is possible to notice that you have to push really close to zero, so close to the, let's say, ideal limit, this two pressure temperature difference, in order to achieve really high performance, close to 70% for this precise configuration, while a more conservative value and a more suitable value for our analysis will be between 5 degrees and 7 degrees for the two heat exchangers. So even here, to push the pinch point temperature difference to the technical minimum is not always the optimal solution. A little less, let's say, straightforward is the analysis related to the pressure drops. And this is due to the fact that the pressure drops has a counterbalancing effect due to the fact that if you change and increase the pressure drop inside an heat exchanger which has a two-phase two-phase fluid, you also change the temperature level. So increasing the pressure drop in this heat exchange also decreases the average temperature difference between the two fluids inside the heat exchanger. So we have a sort of opposing effect on the total heat transfer surface. In this case, let's say the effect related to the velocity, and so the increase of the transfer coefficient is greater, is more significant than the one of the pressure drop in the two-phase conditions. So it is possible to notice that also for the pressure drops, generally the lower, so the faster the fluid, the better is going to be the round trip efficiency in this case. Finally, a brief comparison between the three different fluids that we highlighted. Just to remind that Novec is the one that is going to be tested, and we selected mostly because it's the one which has the lower flammability index. Then the cyclopentane, which is the best trade-off between cost, let's say total heat transfer surface of the heat exchanger and performances. And finally, octane, which is the fluid that we selected with, let's say, low NFPA indexes, so health and flammability, but good performances. In this case, it is possible to see that by comparing the three different fluids, always the optimal of the index between RT, so round trip efficiency, and total heat transfer surface is achieved adopting cyclopentane. So cyclopentane, let's say, at least from this kind of analysis, results to be the optimal fluid, while it is possible to obtain higher efficiency with octane, but only with really high heat transfer surfaces, due to the fact that we have to achieve at least round trip efficiency above 60%. And we have also to notice the fact that the use of octane leads, due to a high critical temperature, leads to subatmospheric condensation pressure, and so to a more complex kind of system that will increase even more the cost in order to avoid the leakages of this working fluid, air in leakages of air inside the condenser. So this would definitely be something not really feasible from a technical point of view. Let's say the analysis on the Novec leads to practically the opposite kind of consideration, so a more, let's say, cheaper system, more cost effective, which is then able to achieve a really high efficiency only at the price of high heat transfer surface, and so a high capital cost of the system. If you want to have more information about the results of this analysis, they were published on the Organic Rankine Cycle conferences of last year, while the analysis of the pre-selection of the working fluid was published at the ASME Turbo Expo of 2023. So, related to this, we can just, let's say, gain some conclusion that first, that is the, let's say, part that we understood while trying to perform this work is that the simulation of this kind of system is not a simple task due to the fact that we have to couple the transfer surfaces of the charging cycle to the one of the discharging cycle. And this leads to a high iterative process when the optimal COP, the optimal performance of the heat pump, are not always leading to the optimal performances of the organic rankine cycle. Second is that the boundary condition that you're selecting and the large number of alternative configuration, alternative parameters that you can select, and the working fluid that you can consider leads to an optimal design of the system, which is even more complicated. So the number of variables to consider is huge, and the optimal design is strongly case study dependent. Second, the fact that this kind of system still can reach competitive round trip efficiency even by considering only latent thermal energy storage, and this can be achieved but at the price of really expensive heat exchanger and really large heat transfer surfaces. So more reasonable value, if you are considering just the temperature range that we consider and just the technological solution that we consider, is more related to 40 35%, even considering cogenerative system. Finally, a last point that we want to highlight is that the choice of the working fluid in terms mostly of critical temperature, which is the parameter which is mostly affecting the performance of the system, can dramatically affect both the performances but also the system cost due to the high pressure levels and the higher cost of the heat exchangers. Future activities related to our task and related to the project itself is going to be the design of these solutions for small size system, so considering also reversible volumetric machines, and also for large scale system, so maybe considering the trade-off between considering couple or decoupled system. Then, obviously, as Professor Astolfi was saying, the testing of the reversible organic Rankine cycle will be performed starting from the summer here at Polimi Labs. And the next, let's say, the final step of the work is going to be to consider a real cases solution with different use cases that Francisco briefly introduced to you in 6 different locations. So these cases will be considered just from a virtual point of view, but where each of them is going to receive a precise design of this kind of system. Okay, thank you for your time, and we are still here available if you have any question.
Yeah, thank you, Marco and Dario. Thank you for this great presentation and this detailed overview about different system configuration of Carnot batteries, and also for explaining the results of case studies conducted within Restore. Also, yeah, as you mentioned, a reversible organic Rankine cycle will be there will be a prototype developed within Restore and tested, and we will see how it will perform in combination with the thesis prototype. So with this, I want to announce the last point on our agenda for today, which is the Q&A session. The Q&A feed is still open. If you want to post your question, you can do it now. You can also interact directly with our experts if you wish by raising your virtual hand. Then we can enable you to unmute yourself and to turn on your camera. The Q&A section will be moderated by my colleague Manisha Rana. So I hand over to you for doing the Q&A section.
Thank you, Thilo. Since we have limited time, I'll start right away with the first question, and that is, what are the main advantages of the Restore solution compared to other storage solutions like water-filled thermal storages or electrical storages? Maybe Francisco, you could answer the question.
Yes, of course. First of all, it's important to mention that in the case of Restore, we are not only storing heat or electricity, like in the case of the batteries, we store both, and we are able to dispatch heat and electricity on demand, and that's important. And on the other part, we are researching on thermochemical materials, because a part of the energy can be stored as a seasonal, in seasonal based storage. That is the part that is related with the thermochemical reaction, and thus the thermal losses of that part are decreased in long periods. Of course, other thing that we are researching are the thermochemical material, because we expect to have high energy densities, But as I mentioned at the beginning, we are in a low level, so we are working on that and making research on that. So thank you for your question. Yeah.
Thank you, Francisco. The next question is also probably addressed to you, and that is, how will the future developments in the energy markets, such as rising shares of renewable energy sources and increasing fluctuations in electricity prices, influence the need for the restore solution?
Yes, of course. What's expected, as I tried to mention at the beginning of my presentation, is that the local governments and also the regional governments are pushing with policies for the decarbonization of the sector, which implies increment the renewable energy sources. In that case, there is a need of new solutions for energy storage. And of course, it's an opportunity for systems like Restore, but also other ones that will compete in this race that is expected during the next years.
Thank you for the insightful response, Francisco. The next question is about the thermochemical energy storage, and that is addressed to you, Andreas. And the question is, could the thermochemical energy storage developed in the Restore project also be used for other discharging and charging temperature levels?
This is possible, but using other materials. For instance, for the calcium chloride, we have higher temperature levels. Of course, there also exist other solutions, but there may be, if you think about the suspension reactor, there is some limit due to use of mineral oil or synthetic oil up to certain temperature levels of, let's say, 300 centigrades, maybe.
Thank you.
Thank you.
Thank you. Sorry, I just checking if there's more questions in the question and answer section. The next question is again about the thermochemical energy storage, and that is, are there possibilities to lower the fraction of the required silicon oil for the thermochemical energy storage?
Yeah, as I told to you, maybe I didn't express it very clear. Silicon oil is necessary only for certain applications. So, for instance, to prevent foaming, and I think, but I'm not sure in the moment, even for reducing the effects of agglomeration, it's necessary to have a certain amount on it. Due to price, we are not really not really happy to use too much of it. So we try to reduce the amount as much as possible.
Thank you for the response. And the other question is also about the oil, and is it possible to lower the fraction of the suspension oil used in the thermochemical energy storage?
Generally, of course, we try to reduce the amount of oil which has to be used. The amount of oil to cover the material in the storage, the values I said to you are first indications. In a continued development process, we will try to reduce that, even the space of the reactor which is required. So, for instance, if we have more knowledge about the heat transfer coefficients, as Dario mentioned, the size of the reactor will be reduced, amount of oil to be used will be smaller, and this will be the tendency of development. Thank you.
Thank you for the insightful response. The next question is about the Organic Rankine Cycle, and that is for you, Dario and Marco. You have presented different options for heat pump, Organic Rankine Cycle combinations, such as reversible cycles, coupled cycles, and decoupled cycles. But why is there a limitation of this 500 kilowatt thermal power for reversible cycles. This was one of the disadvantage you mentioned.
Yeah, I mean, the main point is that for having a full reversible organic Rankine cycle, you also need a machine that can operate as a compressor in heat pump mode, as an expander in a discharging mode. And this could be obtained only with a volumetric machine, so scroll, screw, piston, or other architectures, but not based on turbo machineries like centrifugal compressors, centripetal or axial multi-stage turbines, because they are not reversible. And in this framework, volumetric machines are not really suitable for powers above a certain threshold. So if you are going over 500 kilowatt, the advantage in using turbo machinery in terms of efficiency and flexibility is much higher. And thus, using a fully reversible cycle for a 2 megawatt, using a very big, heavy screw expander compressor is likely not the most cost-effective and best solution from techno-economical standpoint.
Thank you, Marco, for clarifying it. We are approaching the end of the scheduled time of this webinar, so I would not mention any further questions today. So if you have any further questions regarding any topic, you could always contact us, Solites, as a dissemination and communication partner of the Restore, or you could also write to the speakers directly. So I will wrap the question and answer section for today and give it over to Thilo to wrap up the webinar today. Thank you.
Thank you, Manisha. And yeah, to conclude today's webinar, Restore is an innovative concept to integrate various renewable energy sources into current and future district heating and cooling networks. And of course, the efficiency and the competitiveness highly depends on the thermochemical energy storage and the reversible organic Rankine cycles, and both will be tested in combination in the lab. So we can be excited about the last 18 months of the project. And yeah, of course, I want to thank you for your attention, and please stay updated for upcoming webinars. There will be upcoming webinars about the Restore virtual tool, also on the use cases, different demonstrators developed, and many more. So stay updated, as well as about the latest developments. We have a project website and also a LinkedIn page where we post regularly our news. Also, I want to create awareness about the user community. So yeah, you can register there to be among the first users of the online Restore virtual web platform. So this is an interactive experience to discover the Restore virtual tool, as well as the different component models, and to perform a simulation for own use cases. So you can follow the QR code to join the user community. I want to thank to all of our experts for their great presentations, and also a thanks to the audience for joining today. And I hope you enjoyed it, and you have received many useful information, and I hope you will follow the developments of the projects. So thank you all, and enjoy the rest of your day.
Thank you very much, Tilo. Bye bye, everyone. Thank you for your attention.